Plasma, heat, and shockwaves, the hidden physics inside modern missiles. When a vehicle travels faster than 5 times the speed of sound, it does not simply move through air. It reshapes the air itself. Invisible walls of pressure form ahead of its nose. Temperatures climb into the thousands of degrees. Molecules split apart. Electrons are stripped from atoms. And suddenly, ordinary atmosphere becomes plasma. This is the hidden world inside hypersonic flight, where plasma, heat, and shockwaves dominate everything. Modern missiles operating at extreme speed exist inside this violent physical environment, and understanding it requires stepping far beyond traditional aerodynamics into thermodynamics, gas dynamics, and material science. At normal aircraft speeds, air behaves predictably. Engineers treat it as a smooth fluid that gently flows around wings and fuselages. But at hypersonic velocity, air no longer flows. It compresses violently. When a vehicle exceeds Mach 5, pressure waves cannot escape forward fast enough. Instead, they collapse into a bow shock just millimeters from the vehicle's surface. This shockwave acts like an invisible energy wall, converting motion directly into heat. The faster the vehicle moves, the stronger the shock becomes, and the more energy it traps against the structure. This heating is often misunderstood as friction. In reality, friction plays only a small role. The dominant source of heat is compression. As air molecules are forced together at several kilometers per second, their kinetic energy transforms into thermal energy. Engineers calculate this using stagnation temperature, which increases with the square velocity. At Mach 7, stagnation temperatures exceed 1,500 degrees Celsius. At Mach 10, they approach 2,500 degrees. At orbital re-entry speeds near Mach 23, temperatures can exceed 7,000 degrees Celsius. These values are high enough to dissociate oxygen and nitrogen molecules and ionize gas completely. Once air becomes ionized, plasma forms. Plasma is often called the fourth state of matter. It consists of freely moving electrons and charged ions. This plasma sheath surrounds hypersonic vehicles like an invisible cocoon. It glows due to excited atoms releasing energy as light. More importantly, it blocks radio waves, creating communication blackouts. This is why spacecraft lose contact during re-entry, and why hypersonic vehicles must rely on inertial navigation rather than external signals. Inside this plasma layer, chemistry itself changes. Oxygen molecules split into individual atoms. Nitrogen dissociates. These atoms recombine on vehicle surfaces, releasing additional energy in a process called catalytic heating. This adds to the already extreme thermal load. At the same time, pressure near the stagnation point can rise to several atmospheres in milliseconds. Heat flux can exceed 1,000 watts per square centimeter. These conditions rival those inside rocket combustion chambers. Shockwaves are not just heating mechanisms. They also control stability and lift. At hypersonic speed, shockwaves interact with boundary layers, creating turbulent regions that can destabilize flight. Small disturbances grow rapidly. A tiny surface imperfection can generate large oscillations. Engineers must design vehicles that remain stable while surrounded by chaotic, high-energy airflow. This requires advanced computational fluid dynamics and wind tunnel testing at speeds few facilities can achieve. The shape of a hypersonic vehicle is dictated by shockwave physics. Sharp noses place the shock directly on the surface, maximizing heat transfer. Blunt shapes push the shock outward, creating a buffer of hot gas that insulates the vehicle. This counterintuitive principle is why re-entry capsules and hypersonic glide vehicles have rounded leading edges. By controlling shock standoff distance, engineers reduce peak heating by hundreds of degrees. But shape alone is not enough. Materials must survive environments hotter than molten metal while remaining structurally sound. Aluminum melts at 660 degrees Celsius. Steel weakens above 1,200 degrees. Titanium alloys degrade beyond 1,600 degrees. Hypersonic vehicles exceed all these limits. This is why they rely on carbon-carbon composites, ceramic matrix composites, and ultra-high temperature ceramics such as hafnium carbide and zirconium diboride. These materials can withstand temperatures above 3,000 degrees Celsius while maintaining strength. Some designs also use ablative layers. Ablation works by sacrificing material. As the surface heats, it slowly burns, vaporizes, and flakes away, carrying thermal energy with it. This technique was used on Apollo capsules and remains critical for extreme re-entry environments. Each millimeter of ablated material absorbs enormous heat, protecting the structure beneath. Control is another extraordinary challenge. At hypersonic speed, A millimeter of fin movement can generate tons of force. Too much input causes structural overload. Too little causes instability. Flight computers must adjust control surfaces hundreds or thousands of times per second. Human reaction times are far too slow. This is why modern hypersonic systems depend on autonomous control algorithms and increasingly on artificial intelligence to maintain stability in rapidly changing flow conditions. Propulsion also changes in this regime. Conventional jet engines cannot operate beyond Mach 3. Hypersonic vehicles relied on rocket boosters or scramjets. Scramjets, or supersonic combustion ramjets, have no rotating compressors. Instead, the vehicle's forward motion compresses incoming air. Fuel is injected directly into the supersonic airflow and ignited. Combustion occurs in milliseconds. Internal temperatures exceed 2000 degrees Celsius. The margin for error is microscopic. All of this makes detection and tracking difficult, not because of secrecy, but because plasma and shock waves distort sensor signals. Radar must interpret reflections from a glowing ionized envelope moving several kilometers per second. Infrared sensors see intense thermal signatures that change rapidly with altitude and velocity. The physics itself complicates observation. Despite the focus on missiles, these phenomena extend far beyond defense. The same plasma, heat, and shockwave physics govern spacecraft re-entry, experimental spaceplanes, and future hypersonic transport. Researchers are already exploring vehicles that could take off horizontally, accelerate to Mach 15 in the upper atmosphere, and land thousands of kilometers away without entering orbit. These systems would blur the boundary between aviation and spaceflight. Scientists are also investigating plasma flow control, where electromagnetic fields manipulate ionized air to reshape shockwaves and reduce drag. Others are developing adaptive thermal skins that change properties with temperature. Some laboratories are experimenting with self-healing ceramics that repair microcracks during flight. Artificial intelligence now designs hypersonic shapes by analyzing billions of simulated airflow scenarios, optimizing geometry faster than human engineers ever could. What makes this era remarkable is that humanity is learning to operate routinely inside extreme velocity environments. For most of history, transportation speeds were limited to tens of kilometers per hour. In just over a century, we progressed from propeller aircraft to orbital spacecraft. Hypersonics represent the next leap, where atmospheric flight begins to resemble spaceflight in both speed and complexity. The deeper truth is that plasma, heat, and shockwaves are not obstacles. They are signatures of stored energy. Velocity itself contains power. When released, it reshapes matter, ionizes air, and forces innovation. Hypersonic engineering is teaching us how to manage that energy safely and predictably. Modern missiles are simply the first visible application of this knowledge. The same physics will power future spaceplanes, ultra-fast cargo transport, and perhaps one day point-to-point passenger travel across the planet in under an hour. Plasma envelopes and shock layers may eventually be actively controlled, turning what was once destructive into something engineered and stable. And this is why hypersonic technology matters, not because of conflict, but because it represents humanity's growing ability to master extreme environments. It connects air and space into a single continuous domain. It drives breakthroughs in materials science, artificial intelligence, and computational physics. It marks a moment where speed itself becomes an engineering medium. If you want to understand how plasma control could reshape aerospace, how AI is designing vehicles faster than humans ever could, and how hypersonic science may soon transform global transportation, stay with the series. Because next, we dive into how artificial intelligence and hypersonic physics are merging and why that fusion may define the future of flight.